think that if we went in September, it would have been any bigger. But so one thing I've tried this semester that's a little different is I pretty much spent 2 lectures on each topic. And I think that in terms of you guys remembering, if I just give 1 lecture on something and then move on, the risk of remembering a lot of it is reduced, I think, as opposed to if we cover it kind of twice, just at different levels. So, I mean, I definitely welcome you guys' feedback when we're done. But I think that it was worthwhile to spend just a little extra time. I brought some example because on Friday I had some good question about the difference between brazing and welding. And as I mentioned, we're going to talk about how you make chains, how you make pipes. So this should complete today the welding stuff. The first thing from Friday is the question of fusion. If you remember when I discussed this, we were essentially, and half of you were already preparing for an exam or in the weekend, so maybe I need to recap a little bit for those who weren't here. What you're looking at here is a cross section of a joint, and if I make the whole joint, you have the cord here, and I had that all laid out, and then you drop a solid bar on top of it, and then you come and you do the welding here, and what you're hoping to get is to fuse the base metal here and fuse it to the bar to make a good joint. And what that is used for is essentially a complete joist. You could make it this way. A roof joist that is used a lot in buildings. So you got the diagonals here. And that solid bar is essentially the diagonal. So you take a very long run of pipe and you can actually, sometimes they just bend it. So it's a one piece and it's getting welded against the core. And one way to weld it is just essentially, if you look at this locally, what happens is you have the top surface, and now we're looking on this plane. And the bar is on a flat, and then it goes as a diagonal. So there's a little bend into it. You do the same here, and then you go back and forth with that same bar. And this is the cross section that we're looking at here. The reason why the welding, and again, this was the repair welding, the qualification for the repair welding. So the original job was actually much worse than this. Probably pull out one image. Today is a full class. All right, so now maybe you have a little better idea of the overview and kind of the details here. That is the flat portion I was referring to with the weld on it. And what you can see, if you don't have the fusion, you can disconnect the two pieces of metal after the fact. And you're left with the original profile of the steel. Now, there's a little bit of corrosion, and we discussed that, but the main idea is instead of fusing, you just deposited metal on the original tube. And that's just not giving you the strength that actual welding would do. You essentially have a bonded interface as opposed to really having a fusion, having a single piece of metal. So again, that's the difference between fusing here. You see, this is an etched configuration, and here it's unetched, and you see the original shape of that rectangular tube. So if I do the bad weld on the other side here, it just looks like this. One of the reasons, as I mentioned, why you can get to this situation is you know it's going to be harder to melt this component here, the solid bar. So one way to deal with this situation is you put more heat into it. But if you exaggerate, in the end, you will not melt the other piece. And that's what was happening both in the original fabrication and in the repair. So that was from last Friday on the issue of fusion welding. It happens a lot, and that's what I was just going to go through a little bit today. These are diagonals again, so they essentially connect their tubes instead of being round bar, and they connect the cords. They transfer the shear force, but there is tension into every other one of them. And what you can see at the bottom here is, again, original surface from the mill of the steel. So you came and you had a deposit, but it just never really fused this bar, and therefore it's very easy to pull it down after the fact. There's a little bit of fusion here. You see it took a bite out of the member. So if we look at this joint, we could say maybe, 5% of it was fused, which is very little. It creates a situation where you have a pre-crack, and it's easy to fail. Now, one thing that I mentioned is it's not unusual not to control too well the quality of these joints, because the demand on them is not super high. Most of the demand is on the lower chord in tension and the upper chord in compression, and you just need some strain. You can even break, want to take away, let's say I cut this diagonal here, should be fine still, it's not going to fall. If I cut the first one, that's another story. So the welding for the first diagonal is done differently than the other diagonals. And let's look at the first diagonal. So this is actually a scoring facility that was recently built. And they had issues under snow loads. Started to have these big joists. These are relatively large, about 3 feet high joists failing. And what you're looking at here is the end of it. So it's this first diagonal linking the tension cord to the corner. So these again, they roof. So the load comes this way, just a distributed snow load, which leads you to the tension here, and then you have compression on the upper chord. And everything here is working, so you got tension on the first diagonal here, and then it goes tension to compression. It's alternating. It's difficult to make those welds because what you can see is the solid bar is getting between two angles. By the way, the reason we do all this is efficiency. Instead of using a rectangular tube like we had in the greenhouse, we're looking here just at solid bar coming between two angles. So our design here is slightly different. For the first diagonal, it's two angles back to back. And then I got the round bar that's essentially acting also as a spacer. With the way they build it is they have a rig, they put this side, they put the round bar diagonals, and then they put the other one, and they come from under, and they try to do these welds here, and they try to fuse this whole zone. And that is your fabricated joist. What you can see from looking from under here is there is a gap between the angle bar and the weld. So this one broke. There's nothing that really failed because it was still holding on the other side. But if you have two connections, you have two welds, you have one that broke, and the reason is it never fused. So it's essentially like this on one side, and it was just melted with this, but you just had a kind of a brazing interface on the other side. Now, this project, of course, they wanted to know if they had to replace everything or if they could continue. So what we had to do is go with Boscope to try to inspect in that upper corner. It was very easy to inspect this area with the lift. We were just looking from under at the quality of the weld. What was more difficult was to look in this area. You can see on the photograph to the right that you have the roof, and you don't have an easy access. We actually don't see the weld there, but the weld is there, so we had to just come with a camera. With the camera, the idea is to look for fusion. So I'm taking just some example here. If I'm looking at this one, I see fusion. If I'm looking at the top one, I worry more. Now, why do I say I worry more? Okay, so let's take that detail again. The fusion is very important. I brought some samples for you guys to look at of what is good fusion. I got the bar, so if I'm coming in and I'm looking at this and I see the weld just like this, I know that essentially I was oriented and I was providing heat here and I'm going to have fusion there. I don't know if I'm getting fusion on this side. On the other situation, if I'm looking at this and I see kind of a ridge like this, something like that, I know that at least I was giving some fusion on this side, and therefore I'm not worried about the lack of fusion there. So there's it's not in AWS, the American Welding Society. It's part of an ISO standard where the only thing you look at for kind of quality of fusion is that angle between the base material and the welded bead. And when you reach 90 degrees, you just can't guarantee you have fusion. So over here, we have, say, 100 degrees at this included angle. And that is kind of if 90 degrees is the very, very bare minimum in the categories of the ISO standard, 100 is just a little better. And when you're looking at 110 degrees to 120 degrees, there's really what you would like to make sure that you have the fusion. Now let's pass some of this around. There's very little area that I worry about the fusion here, but there was one that I looked at and I wasn't really sure. Look at this spot here. You can see that it was really welded this side, so this would be the one spot that we'll have to check, and I mark it. Yeah. At that corner, we're looking at the outer weld as being the one that, you look at it from the side, it's probably 95 degrees. Be careful with it, but it's not super heavy. I'll pass around the example of brazing. So I was mentioning about the socket joint. This was essentially a pipe elbow going into a straight pipe. And what we did is we cut it in 3 pieces and then we flattened the joint. It just undid. So what you can see is you can see the copper, the original copper, and what you're looking at is the soldering alloy. They go like this, and it's not a perfect joint. It's very rarely a perfect joint. Typically, you try to have 70% of the area where it's really bonded between one side and the other. And what you'll see in this joint is a lot of little cavities, and where on none of the side you can see the solder, so you know it wasn't bonded. When it's shiny on these example, normally it's when you didn't have enough. So you're only touching one side. It made this very nice surface. And the places that were really providing strength and also the seal resistance, they will look more dull because when it stretched and failed, it makes a dull surface here. So just to recap on the welding process, it's efficient. On Friday, we went through the different processes. We had the stick electrode first. Then we were looking at using a metal wire. And then we were looking at using a tungsten electrode, which allows you, if you remember, to be very, very much more precise and delicate. So you can make a lot more refined joints, but it's not as efficient. The submerged arc welding, I mentioned it because you guys now know a lot about heat treatment, and what happens in submerged arc welding is you put a blanket, you put sand over your welded joint just after you did it, and that will reduce your cooling rate, so you're less likely to form martensite, for example, to form a hard zone. What I've shown both on Friday and today is the importance of looking for fusion. The codes will say lack of fusion is not acceptable, and then it becomes on the shoulders of the inspector to determine whether you had it or not. It's very hard to verify it, especially when you're looking at these complex joints. There are a lot of non-destructive technique using ultrasonic, using magnetic particle that will tell you on a groove weld and a nice flat weld, it will help you determine if you had a problem or not. But when you're looking at a little detail like this, it's very difficult to come with a tool and see if you had fusion or not. So it's becoming more of a visual criteria, looking at the angle. All right. Now, what happens when you weld in terms of the properties? You save money, but at the same time, in general, I would say almost 100% of the time, you don't get exactly as good of a material property when you're done. So that's what we're going to talk about more. And there are two main effects. Two or three, depends. The very first effect, if we take, let's take a groove weld first, which, like we discussed Friday, the groove weld, you do a preparation on one side, and then say you have a flat second side. And I'm going to make it more complicated here. I'm not making it a full penetration weld. So I'm ending here with a weld that looks like this. After everything is melted, this is the joint that I was able to do. We refer to this as the root. And then we have toes here. Now, I melted this. So I know that I form essentially a casting here. I'm going to have dendrites. I'm going to have some segregation. One thing that we were talking about Friday in details is we need to protect that molten metal when it's melted. We talked about slag, which essentially will help keep the purity in the alloy. So any impurity is attracted by the slag and will be on the surface here as you weld, or you use a shielding gas so you don't have contaminants coming into your melted pool. So that's really important, and it's only affecting the strength of what's being melted and the ductility of what's being melted. And the thing that we need to start talking about today is that heat affected zone. The heat affected zone essentially starts in a portion that's not melted. So the abbreviation for it is just HAZ. And any metal, it could be aluminum or steel, they both have a heat affected zone. That heat affected zone is very different If we think about steel, we're thinking about, oh, I'm heating him up, and I'm going to quench it, because when I heat it up quickly, and when I cool down, I have all that mass of steel on each side to essentially pull the heat away and gets you a very fast cooling rate. So it's very similar to quenching. And if you remember with steel, what I said is you quench and you're going to form a hard face. You're going to form martensite. So it will happen if you have some alloying element in your steel, if you have high carbon. If you're using a very typical structural steel, it's not bad, because if you remember what I said is you have to quench quickly if you're going to reach that martensite. So if you have an alloy that is just essentially plain iron and carbon, low carbon content, you can essentially reach this low temperature state without transforming a martensite. It's going to be a very small transformation. Maybe you have a little bit of a strengthening effect because you were cooling quickly. So you're going to have a fine pearlite, for example, but it's not going to be too hard. Now, as you go in strength with your base material, you're looking at low alloy steel, so you have chrome, you have a nickel in it. Then that's where you worry about your cooling rate. That's why you can use submerged arc welding, where you can have a blanket on the surface. Or you may need to preheat. If I preheat this, of course, the whole surface, my cooling rate is going to be reduced. So people tend to do that. And the last option is say, well, yes, I formed a hard face. I hope it didn't crack, and you can check for cracks, and you do what we call a post-weld heat treatment. So these are options for you for steel. With aluminum, it's slightly different, because if you remember aluminum, when you quench it, you just freeze the microstructure, and then you go and age it. So what you lose in the heat-affected zone with aluminum typically is that strengthening effect. So you're going to remelt these fine precipitate that are giving you strength, and when it's all done, you have a low strength aluminum. So if I test the property of these heat affected zone in steel, most of the time it's going to be a much higher strength, lower ductility. If I go to the aluminum alloys, the typical aluminum alloys do have that aging process, and because you lose the aging, then you become much softer in that heat affected zone. So all of this has a lot of consequences when you want to make a structure or a device and say, I'm going to be relying on weld for their strength. So if I'm relying on weld for their strength and I have cyclic loading, that's maybe a little bit beyond this course, but I decided that I was going to cover it briefly. If I have an application where I expect more than one load, which is generally the case, I will be looking at the effect of the strength of my structure, so I put S here, as a function of time or the number of cycle that is being applied in surface. And that's the basis, the very basic fatigue analysis. So the higher the load, the shorter my life is. So say I'm putting a point right here to start. And if I reduce my demand, I'm going to be able to sustain longer or more cycles. So that's what we call an SN curve. And you have it here for a number of conditions. Say we do the weld first down here, and then we'll do the base material over here above. So base and then the weld. That's typically how it's going to look like. A typical value here for steel in the worst scenario, you're only able to put about 2 KSI stress as your allowable. And if you have a base material of steel, you're more looking at 20 of that. Yeah, even more, but let's put 20. So what happened? I lost a factor of 10 in my allowable stress for design. It's not great. And there are a number of reasons. So far we talked about the heat affected zone, but we're going to talk about other reasons why codes. It doesn't mean that this is exactly what happens for every configuration. I've taken for you here the worst design of weld, essentially, which is a fillet weld loaded in tension. But it's not an uncommon type of joint. So it's just to keep in mind that depending on what I do, I may or may not have the loads that I was looking at. If you remember, maybe I bring this on Wednesday, the gusset plate design is really where this all comes into play when you notch a member and you bring it in and you put the weld in shear, essentially. That's how you can start going from that 2 or 3 KSI all the way up to, say you may be able to make a category C. Now all of a sudden you're at 10. So you can make a weld. I'll put another weld here. So that's the weld E, but the weld C will get you somewhere around 10 KSI. So this is the huge range for a welded joint, and really it's a function of the geometry and the loading of how much of a knockdown factor you get. You have these knockdown factor here on the base material too, but those are closer to a factor of 50% change if you're welded or not. Because if it's done correctly, if you have the fusion, you can take a weld and stretch it once. It will take it. The problem is when you start doing it repeatedly. Now, why does it make such a difference? If you weld, you're melting the steel. So if we go back to this here, this is really, really hot, and this is cold. So when I'm cooling off, this very hot zone of steel is going to be shrinking. It's just the thermal expansion or contraction when you're cooling. So you're going to need to have this as the solid here it starts to pick up strength. When it's liquid, nothing is really happening. But when it starts picking up strength, when it's solidified and it's cooling, it will be really pulling on the material. And what you're left with at the very end is tension. So this is in contact here. You're going to get tension in this whole area across the weld and in the heat affected zone. And that's what we're showing here. So this is 2 plates being welded together, and you're looking at the stresses as the temperature is going down. Well, when it's hot, it's a different story. But if we look at the very hand, is where we have all that tension in the center. A lot of times you also have tension in the longitudinal direction. So here we're looking at the tension transverse to the weld, but there's also tension in the longitudinal direction. So what it means, if we think about it, it's not super complicated. That even though nominally on the weld I only apply 2 KSI of stress, very locally in the heat affected zone and in the welded bead, because of that residual tension from cooling, I'm much higher locally in terms of stress. And that's why I'm starting to initiate cracks in conditions where normally I can see, well, there's really not much demand on my structure. Locally there is, and that's how you start the cracks. When the cracks started, they're very hard to stop unless you stop the loading. And that's why, if you could start a crack here in this high tension zone, right at the toe of the weld, which is very, very typical, right here. Eventually, I'm gonna fall outside that zone of that residual tension, but I already have a crack, so the crack's gonna continue to grow. Well, we covered a lot. So, any questions? Because this is very important. Yes.
Sorry. I understand how the cooling of the heat-affected zone basically puts it in contraction means that you're pre-stressing it.
Yep. Yep.
I still don't really understand how the martensite layer forming weakens the.
Okay. So if we go back to, with respect to forming martensite, we almost have to go back to the phase diagram. So, and we're going to do it. So the melting temperature is, say, 1600 degrees C or 1650. And the austenite zone is somewhere around 1000. So at the interface between the molten steel and the heat affected zone, you're right there. You're in this range. It's a liquid in contact with the solid. You're exactly at 1600. But essentially you have a zone going away from the melted bead that is in that range where you form the austenite. When you form that austenite and you further cool down is where you go back to all these transformations that we talked about. So the main idea is you went back to austenite here, and then your cooling rate's going to determine if you're getting the equilibrium phases from it or if you're getting the martensite. And that's where it's dependent on the alloy. Who else? Any other questions? All right. So for steel, the increase in the hardness, yes?
So post-heat treatments, does that dampen out that stress profile that you have significantly?
Yes, you do both. That's a good point. So you can get a stress relief if you're doing the post-well heat treatment. The main reason we do it is try to temper any martensite we can be generating if we're talking about steel. But at the same time, before we get there, we're relieving the residual stresses. And that's something that I realize we don't always teach you, or just give you some numbers, right? The stress relief temperature for steel that's typical is just, I'm sorry if I'm confusing the unit because that's all I remember it. And I translated around 700-800. So it's below the austenite transformation. And therefore, if all you want is relieve stresses from the weld, you can go to those temperatures. Now, if you form martensite at those temperatures, you're also going to temper them. So you're really doing both in this case. The reason why I'm mentioning this about the stress relief is we try for the stress relief to not lose anything we've developed in the steel in terms of strength. So we don't want to go back to an austenite if all we're looking for is a stress relief. And that's why typically we go to a lower temperature and we hold it for a sustained period of time. Yes?
How do you do those treatments on large structures? You can't stick the whole thing in oven.
Yeah, that's right. So if you're going to do a post-well heat treatment, typically you come with torches. And you locally heat the surface. And because now you're heating it all the way through the thickness, you don't mind when you're done just letting it go because it will cool down very slowly. The reason why with the weld it's cooling down very fast is I'm putting heat here when I'm fusing. I could have my hand here sometimes, not very far as I'm welding. And the heat just doesn't get there right away. It's going to get there a little bit after the fact, depending on how much heat I provided. But the steel essentially acts as a very, very strong heat sink. Even more so if it's thicker. So don't be surprised if you ever have to weld something and you're looking at something just like this, so big, that there are a lot more requirements for preheating and post-well heat treatment if you're trying to build up something big, because your cooling rate each time is much stronger. And also each time, if you have a structure like this that has, well, they make it just maybe 10 beads here. If you're putting 10 beads in each time you form a certain contraction, you get a lot of distortion and you get a lot of built-in stresses. And that's something that is typical of a large structure. You get, if you start with a T connection at 90 degrees, you're going to get it at 85 when it's all done. And the only way to deal with that sometimes is to put it at 95 degrees. They do that a lot for metal fabrication. They will anticipate how much deflection you're going to get from the welding. All right, so chains. I was thinking about it over the weekend. This is a lightweight one. This is an aluminum alloy, and you can see on the one side you have a weld. The other side doesn't. So it's made of short segments, and so you start with a round straight bar, and you start bending it. A lot of times you'll get the alloy warm, so you don't cause too much distress, or you don't induce cracking when you make those bends. I've seen this done on very small chains, but also on huge chains, and we'll see that in a minute. So if I start with my round bar, and I go to a certain process where eventually I come and I have the piece meeting each other here. So this is the joint I'm trying to make. Now I'm interested in completing that link. So what I do is I apply a difference in voltage, and I create the same arc. It's the same process that we've been talking about coming up with the welding electrode, except that it's one piece with respect to the other. Now, what is very important in this flash welding is to apply force, because if I'm melting and I just let it go, it's going to drop. But the idea is, as the same time that you generate the arc, you push the two pieces one against each other, and it will create a deform zone. If you look at that chain carefully, after the fact here, you're left with extra metal. So if I have I'm just going to do the interface here. So if I'm looking at this zone, I have one side that has really extra material, and same for the other. So this is my original interface. Now, because it's fused, it's only one material. And my heat affected zone on something like this is going to be on each side. So say what I melted is somewhere like this, and then I got the heat affected zone on each side. Now, the beauty of doing this, yes?
What about stress relief, possibly in steel?
Yeah?
Or strain release, for instance. So if you heat it up, would it just deform sometimes on its own?
Oh, that's a good question. So when you do a stress relief, you will have some distortion, and that's why a lot of times you're going to do it before a final machining operation. So if I want to make a precision assembly and I need to weld it for a certain number of reasons, I make that assembly, I heat it up so I relieve the stresses. When I come back for machining, then nothing happens. Because the problem of distortion in machining is when you have these residual stresses and you machine them away, so you take away the tension zone, and then all of a sudden it's deflecting on you. When it's a complete assembly, it's not a whole lot of distortion, because really you got a zone of tension next to a zone in compression, and they'll essentially just reduce in magnitude is really what happens.
So do you often have cases where people will be welding materials that they did not stress relieve, and the whole structure just ends up warped?
Oh yeah, yeah. And then the question is that deflection acceptable or not? And that really depends on the application. If you're looking at a building structure, you will anticipate that it's not going to fit perfectly, that the welders are not even going to do the things always the same way. And as long as you're close enough to be plumb, you just live with it. You don't make any changes. But if you're going to have an assembly with a bearing, joint or something that just really needs a lot of precision between two assemblies, then you end up a lot of times surfacing the and making the final connection holes, for example, when it's all done. Like gearboxes are a good example of that. It's very complex. You got all sorts of plate. It's all welded. You're all done. So you put it in the oven, and then you do your final boring, so it goes right through it. Yes.
That's a stupid question. Why does the current not go through the other part of the board? Rather, why does it go through the gap?
Oh, you have to put it close, and then it's just the resistance of the steel. Yes, no, it's a good question. Yeah, you have to be really close, and this is a very, very high energy process. When you do it and you're done, the main advantage is you created so much heat. You use that for railroad tracks too, a version similar to this. You generated so much heat that you're not going to have a cooling rate that's tremendously high. So you can take relatively high strength steel and go through this whole process without forming martensite. But if I try to do it the more manual way and have all these beads, I could be left with very, very high hardness in the heat affected zone. Let's go to an example of that now. Okay. Sorry, I really don't mean to do advertisement. I need to fix that, put an MIT on it. Okay, so you can see these are about 4 feet high, 4 or 5 feet high, these chains. And they're made just the exact same way we described, where start with a flat bar, heat it up, bend it over, apply the current, push it, and then you clean a little bit. And you can see it on that chain too, that that extra material here, the burr, if you will, was just flattened up after the fact. And there are different ways to do it. You know, you can really deburr and clean it so it looks flat and you can't tell. But if you don't mind just a little roughness there, that's what you're looking at getting. Now, these chains was essentially a federal investigation where they were holding a production riser for oil and gas offshore, very deep, and there really wasn't any cyclic load in the sense what we were looking at here, but it was a time effect, going over time because the hardness was really high in the heat affected zone. They ended up with cracking that normally wouldn't take place. Now, there was a very specific reason why they ended up with these cracks. So it just failed on one side. If we're looking at it after the fact, this is pretty much the welder joint, and you can see on top, it's not all that great. It almost looks like a brazing joint, right? It's really flat, and you have some zones that are a little bit shiny. You have all sorts of things, but it's not a really rough surface that you'd like to get when you have steel with high ductility. It's not a tear, it's just really a fracture, a straight fracture across the surface. On the lower half, what you have is a pre-crack. So at the time that they had the loss, when everything went down, it was essentially the chain was holding a huge buoyancy can. So if you need to keep things straight down in bottom of ocean, one way is you have those chains and you put a buoyancy can that keeps a tension and keeps things straight. The advantage is you don't need something all the way to the surface. You don't need to build up this super complex structure to keep things in tension. It's just the inverse of gravity to keep things straight. There are a number of reasons why we know that this is the time, this is the size of the crack. At this time and depth, it was the final point before everything let go. One of the first indicators, you see a number of beach marks. The image is not perfectly clear here, but you can see distinctly about 7 or 8 of them very close to the overload line. So that tells you how far the crack went before the final fracture. What's the main consequence of this is we know it wasn't really an overload, because if the chain was able to sustain the buoyancy force when it had a crack about 40% through the cross section, it means you didn't have that much load. Otherwise, it would have break much sooner than that. The reason for the cracking is after they did the shop fabrication, the shop fabrication was essentially the big flash well. They had a problem, and they went back and they did repair welding. So the little lines that you see there are individual passes of welding that they did after the flash welding. And what really happened there is your cooling rate is much faster, and therefore you have a hardness that exceeded the threshold to start having small cracks forming under the seawater and the catalytic protection. So these chains had catalytic protection. And just seawater catalytic protection was enough for the steel was too hard to start cracking, and the cracks grew for about a year and then eventually let go. Yeah, we don't have to. That's these details on the fracture surface, essentially how we can tell that the environment contributed. And that actually goes back to some of our previous discussion about cracking between grains or cracking through the grains and whether the grains are weak or not. So in this case, the grains do become weak because the hydrogen generated, again, by the combination of catalytic protection applied on the chain and the environment. So that hydrogen is preferentially going to the grain boundary because it's an open space. And then it facilitates, reduces the strain, and you can get the cracks to go through there at pretty high speed. You know, it's not super fast in this case. You still need the time for the diffusion of the hydrogen to get ahead of the crack and just start growing it. And it's a reason why sometimes with hydrogen-induced cracking or stress corrosion cracking, the growth of the crack is steady. It doesn't vary very much with the load applied because it's the time to get the hydrogen at the location that determines cracking. So it's a constant rate over time in this zone. So when we do this flash welding, we avoid all these issues. Let's talk about one more example that you probably will remember. It's making pipes. It's not impossible, but it's a lot more difficult to do a pipe without a welded seam. So the most common way is start with a flat product, start rolling it, and then I end up welding the two pieces with respect to each other. It's very, very efficient because you can use all the rolling technology to get the plate to the perfect thickness, and then as you go around, and you're left with that welded seam. Now, it will be dependent on your application. If I'm taking for oil and gas, which I've been doing more recently, say I have a drill string. The drill string is going to be working in tension as I try to pull and push the tubing down. It's going to have torsion on it, and of course it's going to have some differential pressure. So the pressure capability is important, but so is the tension. Now when I have this longitudinal welded seam, it's only going to reduce the pressure resistance. It's not really going to reduce the resistance in tension. So depending on your application, what you're trying to do, whether corrosion is a problem, whether the fatigue resistance is a problem, you may or may not care too much if you had these weld seam because you can do them in very controlled condition. This is a very efficient process, and it's easier to inspect. When I was talking earlier about making the complex joints for the roof joists, there's no easy way to inspect, but here, if I'm just taking a flat pipe and turning it around, I can come with non-destructive technique and continuously monitor whether there's a problem with my welded seam. So cost and the ability to do a lot of quality control are the two main reasons why we use welding a lot for pipes. So I hope that you get both perspectives. So you can see the cost advantage, at the same time you can see a lot of metallurgical consequences for making a welded joints. And I can talk to you for welding for a long time if you want to follow up. The brazing is something we haven't talked about a whole lot, but this is a typical braze joint where I essentially have the casting. If you remember our first class, that's how I make a valve very cheap. And then I got a socket joint into the pipe here, and that's brazed the same way that I circulated it. Now this one just had a burst from icing in the wall. So have a good day. Thank you.